Okay. Hi, everyone. Welcome back to episode 2 of the AI co-learning program. I'm your host, Bruce. So excited to have you all with us again today. And for our first-time audience, co-learning is an open lecture series on AI topics. We bring together speakers from across academia, industry, and applied labs to explore artificial intelligence. And last week in our first session, we explored the fundamentals of LLM inference and reasoning. And today, we're going to go one step further into a cutting-edge area, post-training reasoning models. And our speaker today is Zhu Wang, currently a PhD student in data science at UC San Diego. Wang has a deep background in mathematics, starting from the special use program at USTC, and his research focuses on machine learning and reasoning capabilities in LLMs. We're thrilled to have him here, and welcome, Wang. Say hi to everyone.
Hi, thank you, Bruce. It's good to be here. I watched the first episode and it was really great.
Yeah, thank you.
I mean, I wish I had this when I was in, let's say, college, and it was just going to be super great. So we're going to take things up a notch. Last time, the speaker talked about basic inference and some reasoning topics. So today I will be talking about the most hot area, like in all of LLMs now, which is reasoning. I'm going to go over and share my screen now. Ooh, okay. Just want to make sure everyone can see. All right, give me a heads up if everyone can see the slides now.
Yeah, I think we're good. Yeah.
Yeah. All right. So, let's just go ahead and get started. I'm going to be talking about how we introduce time into LLM reasoning, or more accurately, how do we get LLM to reason? And the most principal component I would say is introducing time into LLM, because in essence, LLM predicts one token at a time, and there's no time component. Everything is instant. So that's the first thing I'm going to talk about. And the second thing is two training techniques, or rather two paradigms: supervised fine-tuning and reinforcement learning. Then we'll wrap things up with DeepSeek R1 as a case study. After that, we'll talk about the very hot topic of inference time scaling, which is sometimes training free, but sometimes you can have a little bit of training there. And lastly, I want to just cool the hype down a little bit and talk about the myth around RL. A lot of recent hypes and how they might have shaky scientific ground. And we're going to finish with open questions and Q&A. So let's just go ahead and get started. Why do we need post-training? Prior to 2025, so earlier this year, before the so-called DeepSeek R1 moment, some major AI labs are already doing post-training. You might have already heard reinforcement learning with human feedback and reinforcement learning fine-tuning. So these rely heavily on the human annotated data, and their primary purpose is to align the machine's output with human preference. For example, we don't want the machine to say anything about making a bomb, right? So that's where our RLHF comes in. And post-2025, we see the model struggling with mathematics and coding. So we want to give them time to think, to actually introduce the thing we all do is to take time to think in scientific endeavor. So that's why we need post-training. And an analogy I would give is it's really unfair to compare how fast an infant learns to pre-training. Someone would say, oh, we must be going the wrong direction because it takes billions of dollars, or at least dozens of millions to pre-train on that model, but it takes a few years to raise an infant. But that's not an accurate comparison, because infant already has innate knowledge, which is biological prior to DNAs. They already lay the ground. They know how to navigate the world since day one. And I think of LLM pre-training as the biological prior, and the post-training is really given the DNAs. How do you get the infant to learn to do certain things, to socialize the infant in a sense. And the current landscape is also scaling pre-training is hitting a wall. Like maybe 2 years ago, we already have model almost as big as they are today. And earlier this year, open source models like R1 has proved that post-training is actually very effective. So there are many things at play here that I'll explain later, but chain of thought is a really important one. It gives the model time to think. So given all these components together, we're finally good to post-train our models to think. So key questions, how do we introduce time? And the second one, what are the current paradigms in training them to reason? One of them is RL. So we want to ask, does RL actually lead to generalization? Can models solve problems they've never seen before? And where does the hype outpace science? And finally, we're going to talk about the pathway forward. Okay, so standard inference is atemporal. Effectively, it's a one computational step. You have a prompt, and then it generates the next token. And the next token is a probability distribution. So in a sense, an LLM generating tokens is sampling from a probability distribution. So what is chain of thought? Chain of thought refers to generating intermediate reasoning step before giving the answer. For example, if you were to ask the model what is 1 + 2 + 3, it may generate tokens like, oh, 1 + 2 is 3. So we substitute that in, and then we can do 3 + 3. So you are doing sub-problems in a sense. There's also many other cognitive behavior that can arise in chain of thought. But chain of thought basically is our way of introducing time into LLM inference. So the two popular approach include few-shot prompting. So basically you give the example like the one I just gave into your prompt to, you sort of expect the model to imitate this kind of reasoning behavior. This comes across to many people like pseudoscience, but trust me, it actually works with LLMs. And there has been research showing that few-shot prompting for LLM, for transformers, sometimes can be equivalent to optimizing it with second-order method. So few-shot prompting is one way. And the other way is to actually train the model, to actually change its parameters. You can fine-tune the model on CoT annotated data. For example, we can have a bunch of math problems, and we have their proofs, we have their specific calculations written out in a chain of thoughts, and you just train the model to produce these thoughts. So the effectiveness is primarily empirical, and I have to mention that chain of thought came up in 2022, I think, so it was fairly early. And beyond chain of thought, we can have things like chain of thought with self-consistency. So like I just mentioned, each token is a probability distribution. So you can sample a whole bunch of tokens, let's say 5 of them, and append them to the context, to the prompt, and you generate new distribution. So you have 5 parallel chain of thoughts, and you can have some sort of scoring of voting. Here it's called self-consistency. That means we just take the majority vote in the final answer. So that's one way of doing chain of thoughts. And there's other more advanced ways like tree of thoughts, where you don't generate all the thoughts to the end. Not all of them leads to answer. You sort of explore more possible paths. And I'll mention later that this, or paradigm similar to this, may be the way for the future. Good. Now we can go to the training techniques in post-training. So like I mentioned, CoT came up roughly 3 years ago. So why don't we get it to work? The technique that we have been using in post-training is called supervised fine-tuning. So you have a pre-trained language model, and then you train it again on a labeled data set using supervised learning. So basically, you're breaking up the gigantic pre-training into 2 phases, in a sense, I would say. Because supervised fine-tuning is not that different from pre-training. The really difference here is the labeled data set. And in our sense, we have all the chain of thoughts We have all the solutions, the detailed solution to the problems, and we're teaching the model token by token that you have to imitate these reasoning patterns. And as you can imagine, this is a bit rigid, but that's how we do it prior to 2025. And this is still part of the paradigm, I would say. So a little bit of mathematics here. We're minimizing this expression right here, the log likelihood. So this is equivalent to maximizing the log likelihood, or since log is monotonic, so you are maximizing the likelihood to generate the label, right? And this is the same thing as minimizing L2 norm. If you're familiar with that, that's the square loss. And it's the same thing as minimizing the cross entropy loss. That's for classification. So it really is not that different from pre-training. And reinforcement learning with verifiable rewards. I have to stress this 3 times, verifiable. That's what really got post-training to work in this year. And the key here is verifiability means scalability. And by that, I mean, you don't need a human to tell you whether making a bomb when they're threatened, can the model do that? Like even the person has to judge whether the answer is yes or no. But if you're giving the model a code problem, you can simply run unit tests or compilers and see if the code compile or runs. So scalability here comes from these verifiable rewards. And RLVR in its simplest form is rewarding the model based on binary verifiable checks. For example, does the code compile? If the code compiles, I'll give you 1 in reward. If it doesn't compile, I'll just give you 0. It means you didn't make any progress. Same for math answer. In this way, you can train a model to be, let's say, a calculator. You can just give it a bunch of expression, and once you get it, you can just let the model generate anything. And you don't optimize token by token. Instead, at the end, you check if the answer is correct. I'll incentivize all the behaviors. And if the answer is incorrect, I'll just say, okay, everything up to this point, I will not give you a bonus. It's just a static 0. So that's RLVR. So here is a figure I find on Fireworks AI. Basically, you have training data along with prompts, and policy here is it's a map from prompts to probability distribution. So that means given a prompt, given a context, I can output which tokens are likely here. So that's called a policy. And in post-training LLMs, policy means the same thing as the model. They're really just the same thing. And here you can get the verifiable reward. So this would be a scalar reward. It's a very simple scalar reward, and then you can update the parameters by using gradient here. So that's reinforcement learning. And we've all heard about AlphaGo, the reinforcement learning model that learned to play chess. And what really sets our scenario here apart from AlphaGo is that AlphaGo was trained from scratch. It means it started with a bunch of random parameter and it has no idea how to play chess. And we started training it with reinforcement learning. Notice that even in the case of AlphaGo, the reward is also verifiable. But here, a lot of these math problems are already solvable by the base models. We're really pushing the model's capability up a notch. And later, I will introduce you to a paper that questions into the effectiveness of RL. It says that basically the claim there is RL doesn't really improve the performance, but we'll see the nuance later. And I also want to share this blog by Jason Wei, so the famous OpenAI researcher. It was from a few days ago. So he coined this term verifier's law. Well, in fact, I'm not sure if he coined this or not. But basically, it says the ease of training AI to solve a task is proportional to how verifiable the task is. All the tasks that are possible to solve and easy to verify will be solved by AI. So what does that mean? This really circles back to the thing I said. If you can verify something, that means it's easy to construct a large data set on it. And it is the learning signals when you're doing reinforcement learning will be dense, which means if the model generates 10 paragraphs, it's likely that it will get 8 of them wrong, but 2 of the answers correct. So 2 out of 10 times, you are getting a learning signal. Whereas in the case of AlphaGo, the model can play the chess for, not the chess, sorry, Go. They can play the Go game for a million games and only win 1 of them. So the learning signal is much sparser, much more sparse there. So post-training works really quickly due to this ease of verification. And we can see almost all benchmarks with verifiable questions have already been solved. Whether it's trivia question or exam questions, grad school math, competition math, software development bench, they have all been solved. So it's a strong testament to the verifier's law. Now we're going to go a little bit in depth to the central algorithm, or the most widely used one in RLVR. It's called GRPO, so Group Normalized Policy Optimization. We have to focus on the group normalized part, or a group renormalized or something, group relative. Okay, so some reinforcement learning jargon here. In the case of LLM, action means generating a new token, and a binary reward is what we use here. So in typical reinforcement learning, you have to also train a reward model, because the repercussion of an action is not immediate. You will really have to sort of run it to the end to see what the reward is. So there needs to be a reward model that can predict how well, like how much of a reward we should give to this action at this time. And that is not required for GRPO, which is a core strength in this. So this is, again, with scalability. You don't have to train a separate reward model. And rewards are normalized within the group. This is not necessary, but I'll keep it this way. So another point in GRPO is that you keep the new policy close to the reference the reference model or the reference policy. Okay, so what's the mathematics here? A here would be the normalized group advantage I talk about. This Ri here, this would be so this R here is different from this R. I'm sorry for the notation confusion, but this one here would be the advantage, and this is a very familiar form. So this mu would be the mean of all the advantage within the group, and you're normalizing it with the variance. So this term, after clipping, after weighted by importance. So the importance really is the probability mass on the new policy divided by the old policy. And the way and the reason we have this importance weighting is to say, if your new policy deviates too far away from our old policy, we'll have to clip it with this mean function, with this clip function here. So both of these mean and clip here are to assure training stability. The RIT here is the importance, whereas the A is the normalized advantage. Okay, so this term is called a surrogate. This is token level stuff. And in GRPO, for a single, let's say, math problem, we generate 10 sequence, 10 chain of thoughts. In RL, we also call them 10 rollouts. So The first one can have 1,000 tokens, and you would add up these 1,000 surrogates with their per token RL as a regularizer. We'll skip that. But anyway, you'll add up the 10,000 surrogate and you'll normalize it by the sequence length, and you will add this. So this one here is supposed to be an I here. Sorry for this. And you'll add this up across all the rollouts and then normalize by the rollouts. So this is GRPO, and the objective here is to maximize the group normalized advantage. So basically, if you have, I'll just give you an example here. Let's say we have 4 rollouts, A, B, C, D, and B, C, they led to the correct answer, where A and D, they led to the wrong answer. Then the group mean in this group of 4 would be 0.5, and the standard deviation 0.5. So if you normalize the advantage, then the advantage for B and C would be +1, and for A and D would be -1. So the policy would be updated to favor B and C over A and D. So that's what we mean in a group, and there doesn't have to be a judge to tell you whether B or C or A is good. It's computed from a large number of rollouts. And if the number of rollouts is good enough, the estimation would be good enough. So that's a GRPO intuition. And here comes the first paper in our talk today, and it's really it caused a lot of turmoil in a sense, because it showed that you can train a large language model to reason with just one example. It focused on mathematical training capability. And honestly, I was really shocked when I see this. So here the base model is the yellow pillar, and all of these blue to green pillar, they correspond to using a different portion of the training set. So the paper is investigating how much data do we need to post-train our model. And the key finding is, if you look at this pillar here, it would perform almost as good as training with the full training set. So math is a training set. It has 7.5K examples, but they've showed that you can do just as good in accuracy in solving the problem set by training just on one example with reinforcement learning. And the base model here is Qwen 2.5. So I will not comment on this for now, and we'll just see their claims. We'll just get a feeling of what the really cutting edge research in reinforcement learning with verifiable rewards and what they look like nowadays. So here they claim that policy gradient loss is the main driver. So the policy gradient loss would be the gradient flowing through the surrogate term here. And there's also KL loss. And additionally, people would add something called entropy loss to this objective. Entropy measures how spread out your probability distribution is. So the fatter the distribution is, you have a larger entropy, which means more randomness. The maximum entropy is achieved when every token is assigned uniform probability. And when, let's say the model is super certain of its next token, it's almost like a direct measure, it's almost like a point mass, then the entropy would be much smaller. So you could also have an entropy term here to sort of promote exploration. You don't want the entropy to get too small. If the entropy get too small, which means your model is just outputting deterministic outputs. So here they're claiming that promoting exploration, namely you have to sort of optimize for entropy loss, also improves model performance. And I'm sure from last lecture, we've all heard about temperature. It controls exactly this. It controls how spread out your probability distribution is. So so you can also get the model to perform better by just having a slightly higher temperature. That's what they claimed. So if this were to be true, if one example does work magically like this, then learning is likely driven by the model trying out different ways to solve this problem. Because if the model gets the problem correct 10 out of 10 times, then we can circle back to GRPO. Then the reward for every single rollout would equal to the mean. And then the normalized advantage would just be 0. Right. So in order for RL to actually work, you actually want the model to get some of the rollouts correct and get some of the rollouts wrong. So if it does work on one example, that means learning must be driven by policy gradient, by the model trying out different variations. And how do we promote the model try out different variations? You tune up the entropy a little bit. Right. So it all makes sense so far, relying on the premise that one example does work. And this has to do with the so-called re-ranking hypothesis. It means that RL is activating some latent capability rather than teaching the model entirely new capabilities. That means if one example can trigger such broad improvements, then it's very likely that the reasoning path is already inside the base model, that mathematically the base model can produce this chain of tokens, but RL is just sort of reinforcing the model that these paths are good to take, but not really inducing entirely new capability. So that's the re-ranking hypothesis. And there's also this thing called zero RL training. You just do RL directly on base LLM. This is our second paper of the day. And this one is much more legitimate, I would say. So this graph here is the central claim of this paper. I'll have to say all of their y-axis are not aligned, but the thing is, you can see that by training the model with RL directly on the pre-trained model with no SFT phase, you can already get their performance to raise by 20 points. And even for Quen, you can get it to double or even triple in some sense. For Quen 2.5, you can, for the small model, you can get it to triple. And this is achieved with simple rule-based rewards. So the reward design, so far I've only talked about a binary reward design, correctness. But you can also do format reward, where you prompt the model to output their thinking part in thinking token, and to output their thing, let's say, in boxed. So in this paper, they found that if you so the over-reliance on rigid format here can deteriorate the performance. So without format reward, the Quen 2.5 model can do pretty good, can do up to 54% accuracy on average across these math benchmarks. But if you put format reward, I'm pretty sure they use a large coefficient, because, in machine learning, when you have different objectives to optimize for, you have a coefficient in front of it to indicate how important that component is. So if you use a high coefficient in front of the format rewards, then the model is sort of optimizing for the format reward, and it can produce overly long sequence as well. Across all of these papers, you would find that the base model they used is mostly Quen 2.5, and sometimes they will use Mistral and Llama, but a consistent trend is that Quen 2.5 outperforms Llama, outperforms Mistral. And this is not entirely due to Quen's capability, which I'll talk about later. Okay, so we've all been talking about RL. So what about SFT? So in this paper, they also do an ablation study where you can start directly on the base. You can do 100 steps of SFT, then RL. You can do 500 steps of SFT, then RL. So they found that if you do too many steps of SFT, then the model suffers from sort of memorizing the answer. So it's not able to get as high of an accuracy as it would if you were to just train it from scratch using RL. From scratch, I mean from the pre-trained model. So this shows a negative impact as SFT, but this point is up to debate because how to combine SFT and RL is also is a hot topic here currently, and the main takeaway is that SFT tends to stabilize training, but it may cause the model to memorize stuff instead of learning it. So we'll now go over the DeepSeek R1 pipeline, and we can sort of put everything we've learned so far and see how the DeepSeek moment came about. So for stage 1, they use co-start SFT on this base model called DeepSeek V3. This model is the model they use when you don't turn on the thinking mode in the DeepSeek website. And they use co-start SFT to teach the model basic output format. For example, things like you should wrap your thinking in thinking tokens. They don't do, well, it's showing in previous period this is bad, right? But that's what they did in DeepSeek anyway. So method here is you have a very small set of human annotated data set of reasoning examples, basically chain of thoughts. And then you teach the model to imitate this behavior first. That's the stage 1. And the reason they did it, as claimed in their technical report, is that this stabilizes training. That if you were to apply RL directly, the loss curve can get very spiky, and it doesn't really go. The optimization isn't as good, essentially. And the stage 2 here is a reasoning-oriented RL. So here, they have GRPO with rule-based rewards. This is, again, different from the mainstream of using just binary rewards. They have accuracy and format, and also, I think, language consistency in their rewards. Whereas a lot of the subsequent models that replicate DeepSeek R1 or even go beyond it, they used simply binary rewards with some regularization. So I'm not sure if the format checks here is necessary, but in the second one, they did RL on reasoning oriented, basically a lot of math, a lot of coding problems to get the reasoning capability into the model. And stage 3, they have this is what we call a model checkpoint. So after stage 2, the model there you can freeze it and use it. So that model would be, let's just call intermediate model. You would use that intermediate model to generate a whole bunch of reasoning paths. This is called synthetic data generation, and then you would apply a sort of a set of rules to grade these chain of thoughts, to grade these outputs. And then you can select a small batch of golden data for another round of SFT to sort of get the model to actually memorize that, okay, it's good to reason that 1 + 2 is 3. Thus, we substitute 3 into the expression we're evaluating instead of saying that even for 1 + 2, we have to code. So this part is human labor heavy. And as a side note, synthetic data training is sort of the norm of post-training now. You would have you would have a previous checkpoint or a model from outside. Like, I don't know, maybe Gemini can get OpenAI's output to train their model. But that's probably not what they did, but you can, in theory, do that. And that's called synthetic data generation. So stage 3 is this rejection sampling plus another round of SFT. The stage 4 is a final round of RL for all scenarios. So we've only been talking about RL for, let's say, math, but you can really do RL for anything, right? You can have an essay graded. This essay is 8 out of 10. And then that's a reward for RL as well. So their final stage is to do RL on a more diverse set of problems, a more diverse set of problems to align with general preference. Aligning with general preference here means aligning with human preference. So DeepSeek doesn't say something horrendous. That's the final stage. But we still need that. And the key takeaway here is that DeepSeek R1 is trained by cleverly alternates between RL and SFT. So it's sort of like, we use RL to ingest new capability to have it discover the reasoning path. And then you would use SFT to stabilize the learned behavior. So once the model is stabilized with SFT, you can do another round of RL. That's the key takeaway from R1 pipeline. Okay, now, so here is the graph. It's a bit too small, so I'm not sure if you can see it. But if for anyone that can see it, maybe you can zoom in. I'm not sure if I can zoom in here. Oh, I can. Oh yeah, nice. You have V3 base, and like I said, first stage SFT, second stage reasoning-oriented RL, and these are all synthetic data generation. After that, you do another round of SFT here, and the final round of RL to get DeepSeek R1. And interestingly, there's also something called DeepSeek R1 0, where you simply go this route. You take the V3 base, and then you just apply reasoning-oriented RL to get DeepSeek R1 0. In fact, as a story, DeepSeek R1 0 is what they were training. From the beginning, they were training DeepSeek R1 0, and the problem they found is that DeepSeek R1 0 outputs correct answers to a lot of math problems, but the internal thinking and the outputs can sometimes be illegible in a sense. It outputs some gibberish, and they also mix languages from time to time. That's why they need SFT, as I said, to stabilize training. And there's also, as you can see, language consistency rewards, so the model doesn't switch from English to Chinese to Russian. Okay, so that's DeepSeek R1. And now we're moving into another part called inference time scaling. And the definition of inference time scaling I would give is to take a model whose parameters are frozen. So you have the model at home in your local computer. How do you get it to perform better? So that's increasing the reasoning performance at inference time. There's no additional training needed, although you can do some of those and still call it inference time scaling. A few core metrics here. One is pass at k. So you run the model 10 times, and if one of them is correct, then that counts as a success. So pass at k means the probability that you would solve this problem if any of these is correct. Similar for majority voting. Majority voting means you have k candidates and you take the most likely one. Average at k means you average the correctness across k rollouts. So the ideal upper bound for model performance is pass at k when k is large. So let's say k is 64. We're saying if the model can solve the problem, if any of these 64 outputs can solve, it's kind of a success. That would be an upper bound to the model's performance. And a bunch of techniques have been developed for inference time scaling. There's chain-of-thought prompting. So basically, this is for non-reasoning models that has not been post-trained to do reasoning. as we mentioned, you can prompt it to do chain of thoughts, and it will simply do much better. And you can also do self-consistency, which is similar to the self-consistent chain of thought we talk about. You can do temperature, and there's top K, top P tuning, which is mentioned in last lecture. So all of these techniques, we've seen them, and I'm gonna give you guys some new techniques in inference time scaling. So there is this gen select thing from so AIMO is it's a competition. So think of it as a math competition for models. And this algorithm is from NVIDIA. So they did do some training here, but I'll just assume that we have everything trained. And how do we apply gen select? So you have the model outputs K answers, 10 answers, but which one do you choose? The idea is very simple. They constructed a very large data set with all of these data synthetic in the paper, and they trained a selector model based on all these synthetic data. So they're trained on problems like problem, K candidates, and correctness. So the selector model knows what kind of reasoning leads to the correct answer. So it's sort of an inspector of the internal reasoning process. And this is designed to approach the performance of past K. Whereas you don't have to output K answers and checking every single one of them. You are doing K inference in parallel, and then you have the selector model to select just one of them as your answer. Right, so here is how it works. It generates K candidates, and you use selector to select the best one, and then you would return the best one as the final output. And the key point here is once you have this selector model, you don't have to train anything. You can simply apply this to any model, any reasoning model that outputs a chain of thought. You simply run the inference several more times and have the selector to select one for you. So this is a typical example of inference time scaling, and this solution here actually won the 2025 competition. Right, and this is designed to approach past K. And a really nice way to memorize this is gen select turns past K into a deployable algorithm. So I actually added these few slides yesterday after some really exciting advancements from the International Mathematics Olympiad yesterday. I would talk about this new paradigm in inference called parallelism. So parallel thinking of various sorts have been popping up in the past few months. So basically you prompt the model to explore various solution paths before selecting or synthesizing the best answer. And a recent breakthrough got reported yesterday. And the IMO 2025 has been solved by Gemini DeepThink. So Gemini 2.5 Pro, I think it got 13 out of 35, which is not even enough for Browns. But under the same base model, Gemini 2.5, Google has this new thing called Google DeepThink, which they vaguely branded as parallel thinking, and they solved 5 out of 6, and that achieved a gold medal. That was reported literally yesterday. And in coding, Claude Code has been really the top one choice, and it's also reverse engineered to show parallel sub-agents structures. So Claude Code is not a single timeline. Once you give it a task, it would break it down into many parallel sub-agents. So I think of this as a paradigm shift. It's a linear to parallel inference, and then now inference time is a flexible thinking budget. So the model knows how much of a budget, how much compute it should assign to a model, to a specific problem. And here I also said parallelism means scalability. So combined with the thing I said before, You can say that philosophically in machine learning, ultimately scalability wins, but what leads to scalability? And I would say it's verifiability plus parallelism. And this is basically the new frontier of reasoning. You have verifiable questions, and then at inference time, you do sort of parallel inference. And there are speculations on how DeepThink works. I found this on this website here, and they basically propose the following methodology. So there is a thinking budget assigned to the problem when it receives a prompt, and then it would generate many parallel solutions. We don't know exactly how the parallelism goes about here, but then it would have sort of a selector model or maybe internal scoring to rank these paths, and then they can select the best one as the top branch. So they would output that. This is just their claim. I actually don't think it works that way. So this is my own interpretation how Gemini DeepThink might work. So there is definitely initial branching and scoring. So there's definitely their own mechanism of generating parallel path. But then I assume that they would also take these scores and output and maybe select the best reasoning path, and they would append this to your prompt and tell the model, hey, this is my first round of solution, and this is my solution, here is the critique, here's the score, here's how you might want to improve it. And then they may do this iterative process again. This is just my personal belief, but a very new paper yesterday, it also came out yesterday. They showed that if you prompt the model to iteratively refine its approach, even Gemini 2.5 Pro, the one you can access on like Google AI Studio or something, it can also get the gold medal. So my personal belief is that if you get the model to run parallel and iteratively at the same time, then it performs much better. I've also been playing around with models at inference time, and I found that simply by chaining models together, like you can chain Gemini together with Claude, you can have the output of Gemini, you give it to Claude and say, critique this, provide feedback, give it back to Gemini. Well, Gemini does it again and give it, let's say, to DeepSeek, and you can get a model to solve more problems in this way. This is a practical note. And so we've seen a tremendous success so far, and I'll have to cool down the heat a little bit because, well, I found this meme on X, right? So first of all, when we're doing AlphaGo, we are training models on millions, billions of examples. And now we got a paper that training Quen with just one example, namely one-shot RLVR. And there's also paper showing that you can train the model with no example because you can output 10 chain of thoughts and you can incentivize the model to select the one with the highest self-certainty. And certainty can be something measured by, let's say, entropy. So you can literally train a model with 0 examples. How does that even make sense, right? And in April, another paper called Spurious Rewards showed that you can literally give the model any signal. Let's say when the model gets the answer correct, you give it a reward of -1. And when it gets wrong, you give it a reward of some random number between -1 and 0. And it also worked. So it really got us thinking, is the science solid here? Are we all talking about the same model? Are we using the same setup, et cetera, et cetera? So is the hype real? So here are 2 main counter arguments to RL's effectiveness. The first one is incorrect baseline evaluation. So each of these phenomena are proposed from the paper. And in all of these papers, they would have to have a baseline score. Say Quen 2.5 can achieve 60% accuracy on this benchmark. And then after RL on spurious rewards, we got it up to 80%. And the question is it really 60%? Have you optimized for the temperature? Are you using the same prompt as in the official doc? Or there's also something called answer extractor. So when you're benchmarking model against mathematics, the model doesn't just output a number, or sometimes it's a proof, right? Sometimes the answer could be a number, but it's buried somewhere in the whole block of outputs. So you would need to have an answer extractor. Are you using the same answer extractor as other benchmarks, as other experiments? So you can have the same temperature, same prompt, same model, but different answer extractor would give you different accuracy. So is the baseline evaluation correct? And then, as I mentioned, it seems like Quen 2.5 is just consistently so much better than Llama. It's so much better than Mistral. It's even better than DeepSeek math. Does it inherently have stronger math skills? Or has it already been contaminated with benchmark data? That means in training, maybe in pre-training Quen 2.5, the model has already seen some of these problems. So when you're doing RL, you're sort of reminding the model of these problems. And we would see that the answer is yes for all of these. So the scientific ground here is shaky. There's this blog that reevaluated all these papers, spurious rewards. The RL was one example we talk about. And there is large reasoning model self-trained with self-certainty. And the reported gain on, they pick one benchmark, but this works for any just any benchmark. So the reported gain in spurious rewards is 28.5. That's a huge plus. And the actual gain is 5.5. And the reason is that the reason is different for every single one of these papers, but it boils down to the thing I talk about. The paper authors, they didn't use the same set of optimal temperature. They didn't use the optimal prompt. So what we're saying here is you can get the base model to perform almost as good as the RL model they trained simply by tuning temperature, by using few-shot prompting, and by using a more accurate answer extractor. So the gain is not as huge as reported. Sometimes the gain is even negative, for example, in the case of RL with one example. So this doesn't invalidate all the RL research immediately, but it does tell us that the gain may be a few percentage instead of 20, 30% most of the time. But still, spurious rewards, they can get a model to perform a little bit better. You can get a model to perform 15% better with no with no examples at all. I mean, that's not as significant, but it's still very good. And also data contamination or benchmark contamination has been sort of verified for Quen 2.5. And the way they do it is extremely simple. They just take a problem from Math 500, a typical benchmark. They would give the model first 40% of the problem statement and just let the model outputs. And they found that Quen 2.5 can perfectly replicate a lot of these problems. And that just doesn't make any sense. Because from a general language perspective, if there were no data contamination, then given a prompt like this, like the partial prompt here, how could you expect the model to output the example here? Right, so this basically validates that, yes, there is some level of data contamination in Quen 2.5. But I also mentioned that Qwen 2.5 has inherently a bit stronger math capability. That is also true. Oh yeah, also they tested the model on contamination-free dataset, which means they constructed the dataset themselves, called random calculation. As the name suggests, it's just a bunch of arithmetic operations. So the model's ability to calculate. And they did RL on this with all the claimed design, random rewards, inverted rewards, and correct rewards. And yeah, so this is the performance training on their contamination-free dataset. You can see that if you use correct answer, correct rewards, then it leads to steady improvement. Random rewards leads to unstable. So these lines here, they can improve, or they can also decrease a little bit. But if you use inverted reward signal, it leads to model performance collapse. And this is what we're expecting, right? There's no surprise here. And when I say Qwen 2.5 is a little bit better than Llama, is that even when training on this contamination data set, Qwen 2.5 with a smaller number of parameters can still perform better than Llama. So yes, it's indeed better, but it's not that better because it has seen the benchmark, essentially. Okay, so here is a very recent and I would say blockbuster paper that sort of claimed there's no new fundamental reasoning patterns from RL. I have many slides on this. I'll skip. I'll just skim this with you. So they're basically saying that the reasoning path from RL trained models, they are largely already present. Right, this is the claim, the re-ranking hypothesis we've seen before. And they used various metrics to support this. And there's this metric called perplexity. I will simply skip that. But the upshot is that you can take the outputs from the RL model and you can feed that back in. Well, not feed back in. You can see if the base model can generate this response as well. And you can see that, yes, the base model has a non-zero, a non-trivial likelihood of generating this kind of response. And this is not something new because even in 2024, before DeepSeek R1, they have a model called DeepSeek Math. And they've already reported that it seems like RL, the response from RL can also be generated from base model. It's just that RL is more likely to generate the correct answer. Whereas if you give the base model enough trials, let's say 64, 256 trials, then it would likely get at least one of them right. That means, in a nutshell, that base models past K and large K is as good as, if not better, than its RL counterpart. So the graphic representation is just RLVR model is better at sampling these paths, whereas base model, its distribution is more spread out. And but the answer to correct answer, the solution to correct answer, sorry, is already present within the base model. Yeah, so base model's potential at large K, when you give it enough trials, the green line across all these models, they can outperform the RL counterpart. And there's also a subset relationship, which means many of these problems that are solvable by the RL model can also be solved by the base model, given enough tries and better prompting. Okay, so now we're done with all the so-called lecturing parts, and these are the open questions. So how do you integrate the sort of stabilizing training ability of SFT with RL, because we don't see the model solving more math problems from SFT, but we do see that from RL. And well, from the previous paper, it says that RL is boosting sampling efficiency. That's more of a theoretical question, but practically, how would you combine SFT and RL? And also, how would you optimize the RL process itself? So, namely, RL is still inherently very expensive and computational heavy, because for every step of optimization, you would have the model roll out many times. How do we get effective RL training? And then there is a sub-direction called latent reasoning. So all of the chain of thoughts we talk about is in the token space. So you can literally see the model reasoning. But can we prompt sort of design an objective to train the model to reason internally? Because the internal representation is sort of continuous in a sense. It's in the latent feature space. It's a Euclidean space. So there's more capability for thoughts there. Whereas in the token space, it's thinking in human language. So there's latent reasoning. I'll just skip these two papers. They're about effective RL training. The 80-20 rule is basically saying you optimize for the highest 20% entropy tokens. So it saves a lot of computing budget. And selective rollouts basically means, well, instead of having to roll out 100 times for one RL epoch, we have some sort of selector to select only 20 of these rollouts. So we only have to do 20% of computation, etc. These are effective RL training questions. That'll be all my presentation so far, and I'm happy to take any questions.
Okay, thank you so much, Juan, for the amazing talk. So now let's open up the floor for questions from the audience. Please post your questions in the live chat. And just a quick reminder, we will give away 10 OpenRoot API keys to audience today. And if your question is selected, please screenshot your comment in the chat and send it to our official email so that we can verify and send you API keys after the session. Okay, let's see the questions here. So the first question is we have here is, what are the current limits of reinforcement learning for long-term tasks, and how can we break through them in the future?
That's a great question. So I actually meant to mention this in my presentation, because the title is training model to reason and act, but I didn't mention the act part. So the way you induce the model to act is similar to how you induce it to solve a math problem. You would gather chain of actions. You would gather how what kind of tools it should call in, as let's say initial SFT stage. You can gather these kind of data, and this is called multi-turn RL training. You can train the model to on a shorter time horizon task with these kind of tasks. Let's say, let's get it to book a flight for us first, to boost its ability, its awareness that it should use tools sometimes, and then you would have the model training on longer and longer time horizon tasks. But I would say for the really long-term task, like the one we see with Claude 4 coding for 7 hours straight, and that's more of an engineering feat, because it's impossible to fit all the prompts of 7 hours length that would surpass millions into Claude 4, because a key bottleneck in LLM inference or LLM training is the attention mechanism, where the computation scales quadratically if you're not using linear attention with the context length. So there has to be some sort of prompt caching. There has to be some sort of the model knowing when to condense their previous prompts. And there has to be use of sub-agents. They're not using one model. So for long-term tasks, you would have to have a team of agents, and then periodically compacting the existing context, plus the kind of training I just mentioned.
Okay, thank you. The second question is, how do you plan to implement multimodal reinforcement learning?
Multi-modal reinforcement learning.
Yeah.
I think so far reinforcement learning has mainly been done in the space of text, and I'm like personally I'm not an expert on multi-modal training, so I would say from the evidence I'm seeing, simply by training it on text, you can already get the model to do some other sort of task. I'm not sure if you've seen it, but there's a viral video of Claude playing Pokemon and Minecraft for like a few hours, and it does pretty good. And it's like, yeah, I'm not a multimodal expert, but I would not be surprised if reinforcement learning in the text space can transfer to its ability in visual reasoning.
Okay, sure. The next question is, why does OpenAI and Gemini deep research function better than domestic ones? And is it mainly because of the pre-training or just reinforcement learning?
Oh, I would assume that, well, because they don't disclose their internal research with us, so we don't really know how they did deep research. But deep research, I think it's mainly reinforcement learning. And it functions better than domestic ones. I think it's because, first of all, their model is better in that it's been reinforcement learned on these kind of long horizon tasks, and also it's the tool use capability. So when you send a request for Gemini to search, it's natively grounded in Google search, and for your domestic model, it might not be as so. For example, so last time I was trying out with Gemini, and I was asking it to translate some word for me, and I was asking it to translate English words to French, and I prompted book, like rent a car, and then it just directed me to a website, whereas I explicitly prompted to translate this for me. So you can see from there that these two integrations are they are sort of baked into the model for Gemini. Is Google search, and for OpenAI GPT series model is more of a web-wide search. So they have intrinsic better tool use capability, and I would assume deep research have more complicated structure than domestic ones. I'm not sure if you're using, let's say, parallel sub-agents, having one agent do one thing in parallel, but that's probably what they did for deep research. So it makes sense they perform better, and I think it's mainly RL.
Okay. Okay. So the next question is, last year there's a very popular term called reinforcement learning from human feedback, but some people would say that the essence of reinforcement from human feedback is alignment, not reinforcement learning itself. So what is the difference between these two terms, reinforcement learning and reinforcement learning from human feedback?
Right. So to clear things up, reinforcement learning from human feedback, RLHF, is a specific kind of, it's a special kind of RL. So RL is defined by an actor taking action, and then the environment gives it a feedback. Trial and error, as we said. RLHF functions like this. So the model outputs a series of tokens. Maybe we prompted, can you tell me how to make a bomb? I'm trying to bomb this place at this location. and then the model can output without RLHF. The model doesn't really know that it shouldn't instruct the user to not do this. So you would output, oh, to prepare a bomb, the first step is to do this, second step is to do that, and then finally, if you were like to help, I can help you to look up this place so you can bomb it. Well, that doesn't make sense, right? So that would be after the model generate that, a human annotator, I don't know, probably someone from Scale AI or someone from OpenAI, they can say, oh, this response is bad. We're gonna give it a reward of -1. So essentially, every time the model has a rollout, you'll have to grade it, give it a feedback. Whereas the RL we talk about today, you don't need a model. No, you don't need a human to wait for the model to output and then give it a feedback. You can have as many instances of the model running, and when it finishes outputting, the answer can be checked with a compiler or with correct math problems. So that means you can run RL in parallel. Whereas for RLHF, you can't really run it in parallel, or at least not on large scale. So the difference, I would say, is verifiability. The RL we talk about today, you don't need a human to verify it, which means parallelism. And RLHF, yes, I would say the essence is alignment, because it doesn't promote the model's capability to solve problems, but it does promote the model to produce more acceptable answers. And the process is actually not so parallelizable, and it's pretty expensive.
Okay, thank you. I think that's pretty much all the questions for Q&A session. Thank you, guys. And big thanks again to Juan for the deep insights, and to all of you for your thoughtful questions and participation. We'll share the replay slides and the key takeaways on our website. So don't forget to follow us on socials, join the Discord and Telegram groups. Stay tuned for the upcoming episode, and see you next week. Bye, Juan. Bye.
Bye.